Cool. So maybe it's we can start. So it's a pleasure to be back for the last APPROX session of this APPROX random conference. And the first talk of the session is going to be given by Spurti Gunda on the parameterized approximability of contraction to classes of chordal graphs. So Spurti, all yours.
Yeah, thank you. So I'm going to present you this paper, which was co-authored by Pallavi Jain, Daniel Lokstana, Saket Saurabh, and Praful Kumar Tale. So let me start by defining the classes of chordal graphs. So a chordal graph or a triangulated graph is a graph which has no induced cycles of length greater than or equals to 4. And a subclass of chordal graphs is cliques or complete graphs, where every vertex is adjacent to each other, or it can also be defined as a clique is a graph that has no induced P3 or path of length 3. The subclass of chordal graphs split graph, and cliques are the subclass of split graph. And a split graph is a graph where the vertices can be partitioned into two sets, X and Y, such that X is a clique and Y is an independent set. It can also be defined as a graph that does not have an induced 2K2, a cycle of length 4, and a cycle of length 5. So a 2K2 is a graph on 4 vertices with 2 disjoint edges. So, and we were looking at the graph modification problems. So in a graph modification problem, the input is a graph G and an integer K. And we ask the question if we can make K modifications to G such that the resulting graph is in H. So H here is a polynomial time recognizable graph class. And in our paper, the resultant graph classes are the chordal graphs, split graphs, and the cliques. And the modification operation includes vertex deletion, edge deletion, or edge addition, and another operation, edge contraction. So in the edge contraction, we replace the end vertices of the edge, UV, with the vertex W, and we make it adjacent with every vertex that was adjacent with either U or V, and delete all the loops and edges, parallel edges, such that the graph remains simple. So these problems are known to be NP-hard, and these problems also studied under the parameterized complexity. And it was noted that the vertex deletion and edge deletion are slightly easier than the edge contraction. So when the modification operation is only restricted to edge contraction, it makes the problems harder. And we studied the contraction problems under the parameterized approximation. So in parameterized approximation, so the name suggests we also have a parameter along with the input. For example, here the parameter here is the integer K, and we are looking at the optimization version. So the first important concept is alpha FPT approximation algorithm. So this algorithm runs in time f of k times some polynomial in n, where n is the size of the input instance. And if there is a solution of size k to the problem, then we must return a solution with alpha approximate solution. And if such an algorithm exists, then we say that the problem has an alpha FPT approximation algorithm. Note that if the optimum solution, like the minimum solution, is greater than k, then the algorithm can fail. So, and another important concept is alpha lossy kernel. So kernelization. So in this, first given an instance, we try to reduce it to a smaller instance. So the smaller instance here we need the size to be bounded by some function of k. And also, if there is a C-factor solution for the reduced instance, there should be an algorithm that outputs alpha times C-factor solution for the original instance. And if we have such algorithm, then we say that the problem has an alpha lossy kernel. And if the size, like the size of the reduced instance, G prime and K prime, if it's bounded by some function that is polynomial in K, then we say that it has a polynomial size alpha lossy kernel. So an important proposition states that problem is alpha FPT, if it has an alpha FPT approximation algorithm, if and only if it has a lossy kernel. So once we know that it does not have an alpha FPT approximation algorithm, and we can rule out the option of it having lossy kernel. And in particular, we are interested in polynomial size kernel. So we studied the problems under this theory, and these are the following results that we obtained. So for any alpha greater than 1, we proved that for clique contraction. So here the resultant graphs is clique, that it has an alpha lossy kernel of polynomial size. And we proved the similar result for split contraction, but not for every alpha, but it's for every alpha greater than 2. And for alpha less than 1.25, we proved that it does not have an FPT approximation algorithm. So this was done by reducing from a problem that we already know. And so this rules out the option of it having alpha lossy kernel for alpha less than 1.25. And for caudal graphs, caudal contraction, we proved that it cannot have an FPT approximation algorithm for any alpha greater than 1. So yeah, so these were the problems that we studied, and these were the results that we obtained. So it is interesting to know that even though all these graph classes are closely related, they're behaving very differently when the operation is edge contraction. So one of the open question is that if we can bridge the gap for the split contraction. We obtain the result for alpha less than 1.25 and for alpha greater than 2. So yeah, thank you. Questions?
Thanks. We have time for a question or two if people have questions.
So do you allow only contractions or do you allow all three operations?
We only studied for only contraction. So yeah.
So have people studied combinations of the operations?
I'm not sure, but definitely studied for different modification operations. We have results for separately. Yeah.
Thank you.
Cool. Thanks, Purti, again.
Thank you.
And so our next speaker is going to be, I think, Touchful.
Yes. Can you hear me well?
Yeah.
Okay.
And,
cool.
and the slide is very clear. So maybe let's wait until it turns 1:30 just in case somebody's timing this thing. Wants to come in just at the last minute to listen to your talk. Cool. So the next talk of the session is going to be by Touchful, and he's going to tell us about work on pinning down the strong Wilbur one bound for the dynamic optimality conjecture.
All right. Thank you, Anupam. So this is joint work with Julia and Parinya. And yes, this talk is about binary search tree. It's the binary tree such that every node on the left subtree has its key less than at most the root, and every node on the right subtree have its key at least the root. So this is one example. And so you might ask, what is still exciting about BST? What even to do with it? So it turns out that there is something still actually I think very exciting. And also for our Bob Tarjan, it's like his most favorite problem maybe. And we don't need to know exactly what is this conjecture is about in this talk, but people really cares about it, and we try, and many people try to work on it. And if it is true, it will be basically like one of the strongest beyond worst case guarantee for data structure problem. In this talk, we will only look at another problem which is strictly easier. It's called optimal dynamic BST. Roughly speaking, is about trying to compute to find optimal dynamic BSTs. Is not necessary. You don't need to know exactly what it is. You will see why. And this is still like wide open. And this is a step that is necessary for dynamic optimality. And we will focus on this problem. And by the way, I just want to mention quickly that a strictly easier problem called the optimal static BST. This is a very classic and solved long time ago, like almost half century ago. But as this problem, optimal dynamic BST, is still wide open, and we need it. We need to solve it for resolving the main conjecture here. And it turns out that to really look at, to work on this problem, optimal dynamic BST, it turns out you don't need to know anything about complicated data structure, no trees, no pointers, no path or anything, because it has been proved that there is another problem called MinSat, which is a very clean problem and much easier to think about. And I would like to use this opportunity to advertise this problem to this approximation community. So it's a clean problem, and now I want to define it. So it's enough to just solve this problem. All right. So let's see what is this problem. To know what is this problem, you need some concept. So we will have a point of set on a plane, and first I need to say that I define what is mean to say that a pair of points is satisfied. So if you have two points P and Q, if there is another point inside the rectangle defined by P and Q, then we say that this pair is satisfied. The point can be on the corner, on the border, or inside the rectangle, right? Or if it is like horizontally aligned or vertically aligned, then they are satisfied. This is not satisfied. And now the set of point is satisfied if for every pair in the set, the rectangle defined by it is satisfied. Every pair is satisfied. All right, is this clear? Okay. So and this is not satisfied because of this pair. This pair, you don't have another point inside the rectangle. All right. So, and now MinSat problem. In this problem, you are given the set of points, right? In the plane, in the disk, and in each row you have only one point. And what you need to do, you just need to add some more points, y, so that once you look, the y union x is a satisfied point set. Okay, and what you want to do is just to minimize the number of points you add. You want to minimize the size of y. Given a point, you just want to add y so that the point set is satisfied. And what is known about this problem? Log n approximation is known, log n is known. We can do it in polynomial time. Turns out that even for exact case, we don't know NP hardness. And so by the way, this result is basically equivalent to optimal dynamic BST, right? I just want to stress again that if you can make progress on this problem, data structure people will care about it. and we basically asked what can we do between this regime. We make some incremental progress, I would say. So first we said that for constant approximation, which is really the final goal, we don't get a polynomial time algorithm yet, but we can do sub-exponential time algorithm, so something non-trivial. And we proved that for anything better than log n, there is actually a barrier for the known approach. So the known approach cannot go beyond log n. So that is the result. And just very quickly, some statement of the result more clearly. So the first result is actually the trade-off, which actually says that for any k, we can get an approximation algorithm with this running time. M is the number of rows, and this is something exponential. When k is large constant, you get something like sub-exponential time. And when k is log n, you recover what is known, the log n approximation in polynomial time. There are three ingredients. One is dynamic programming. This is straightforward. Then the new one, the new idea is kind of divide and conquer. And the last one is some decomposition lemma. I suggest you look at the full video to know what is this idea. The second result is about showing that there is a barrier for going beyond log n for the known approach. I don't have much time to really define what it really means, but to get this result is by showing that there is some instant x such that the optimal solution, the size of the optimal solution for x is much larger than the non-lower bound, which is called Wilber bound. Is much larger by log n. And before that, people used Wilber bound to give log n approximation. But we show that there is a gap of log n. So that was the only approach that was used, and we show this gap. So now I want to end with some open problem. So yeah, please just look at this problem. It's so simple to define, and how to get beyond log n approximation. We really care about this, and or some hardness result would be interesting as well. Thank you.
Thank you, Kashpo. So quick question. Is there a convex programming relaxation for this problem that is known, that is understood?
There is one some report which use some straightforward LP relaxation, but the integrality gap is very bad. It's not clear how to formulate a good LP or even some convex formulation, convex optimization for that. I'm not sure. Yeah, it might be a good tool. Yeah.
Any other questions for Touchball?
I have a question. So have people looked at higher dimensional analogs of this question?
And not that I know of. Yeah.
So
I don't know. Yeah.
Are the higher dimensional analogs even interesting for the data structures community, or do they care about the two-dimensional version?
So I don't think it has application. So yeah, it's
maybe for NP hardness and hardness, maybe it's easier to think of the higher dimensional version.
Sure, I think so. Yeah.
True.
Thank you.
Thanks. So let me stop sharing screen.
Perfect. Thanks again, Touchable.
Okay.
So the next talk is by Karin.
Yeah.
Karin, you can share your screen now.
Okay. Sorry.
So the talk is by Karin Chubarian and Tassos Sideropoulos about computing by-Lipschitz outer embeddings into the Karin, all yours. Yes.
Hello, everybody. It's a great pleasure to give this talk at the APPROX conference. This talk is based on the joint work by Anastasia Sideropoulos and myself. Both of us are from University of Illinois, Chicago. So first of all, let me talk a little bit about metric embeddings and what they are. Metric embeddings are basically a map from one metric space to the other metric space, the host space, and we would like to know how good does this map perform on preserving some structural properties of the initial space. To see a little example, let's say we have this small graph and we want to map it into a line. We can do it like this. We can do it like that. We can do it in some other way. There are many ways to do this, but we would like to quantify what does it mean to be a good embedding. Of course, there are different notions of good. There could be additive distortion in terms of the distances in the initial object, multiplicative distortion, and probably something else. For this particular work, we are interested in the multiplicative distortion, namely by how much does the final embedding stretches or contracts the distances in the points in the initial space. For instance, in the first embedding, embedding G, the biggest one can check that the biggest expansion the 2 points can get are the vertices V1 and V3, and the distortion is 5. For this embedding, embedding F, the biggest expansion is 2 and no contraction, so we conclude the distortion is 2. The second embedding is better for our case. Why do we study embeddings from graphs into a line? First of all, we used graphs as the initial space because sometimes if a good manifold is sampled under the uniform distribution, the resulting sample space is a graph, and then the shortest path distance in this graph approximates geodesic distance in the manifold pretty well. Why we're interested in the line? Sometimes we want to simplify our initial object in order to get some hidden structure, hidden properties of the data. Perhaps the data has some one-dimensional subspace which can tell us more about its structure. Finally, why outliers? Well, sometimes malicious adversary can spoil data pretty bad with just inclusion of one point. The example would be, this is a simple manifold, a curve. Let's assume we sampled the points. We got the shape, which looks pretty much like the initial curve. But then let's say adversary added just 1 point. And this 1 point messed things pretty bad. If we want to recover the shape, we can get easily something like this, which is very far from the initial object. Let us look closer at the outliers. Why are they interesting? So I claim that even complicated graphs can have sometimes just a few vertices which upon deletion make them into simple objects. For instance, here is this graph. It doesn't look like a line, it looks like a bicycle front wheel. But I claim that it can be modified into a pretty simple collection of paths. Let us assume that it is big enough. It's really long path and really long cycle and really dense wheel. So intuitively, it should have large distortion being embedded into the line. Now assume that we remove just these 2 points. What we get a collection of 3 paths, which have distortion 1 for the embedding, by removing just 2 vertices. Here is the formal definition of what does it mean to admit a KC embedding into the host space. Basically, it means that there exists a small subset of points in the initial metric space such that if we remove them and look at the metric space with the induced metric, it admits a small distortion embedding into the host space. So one could think about what could be the abstractions for the embeddability of graphs. It turns out there are 3 of them. First abstraction is high density regions. The way to think about them is, for example, a star graph or a clique graph. When a very small ball contains a relatively large number of vertices, or perhaps binary tree, when relatively to to the size of the graph, we have a lot of vertices packed to the diameter of the graph. Then we have large metric cycles. So the intuition behind them is just think about one large cycle, but it could be a little more complicated than that. The graph should have a large topological hole inside it. Third abstraction is a large metric tripods. So what are those? The tripods are collection of paths attached to a single point. And this path should be really long. It could be more than 3 paths, but it's enough to consider the case of 3 of them. We need one more ingredient for the algorithm, so-called repairing lemma. Since we're going to get rid of these abstractions one by one, it is not clear what happens with the graph once we deleted an arbitrary subspace of vertices. Maybe it became unembeddable. So here is an example of what I'm talking about. Imagine we have a grid. The grid has constant distortion being embedded into a line. We just traverse the grid like that. Now, if we delete 2 slits inside the grid, we get a cycle, which has distortion theta of n. However, if we remove just 1 point, we obtain a line, a path. And this path it is a line, doesn't have any distortion. This statement can be generalized as follows, that if a graph has low embeddability to begin with, and we removed a relatively small number of vertices, it still has relatively good embedding. Let me give a brief outline of the algorithm. First, we reduce density. This is done, we are applying vertex sparsifier recursively. Then we eliminate metric cycles, eliminate metric tripods, and embed it to the line. I give the details of all this procedure in the long talk for those who are interested. In between those steps, we apply the repairing lemma to see that the number of outliers doesn't blow up. We set the final outliers to be the union of these 3 elimination step outliers. Here is the theorem, the main statement of the paper about the guarantees of the algorithm. And that's it. Thank you so much.
Thank you. Any questions? Maybe I had one, which is there any hope of getting something like this for like the 2-dimensional embeddings into the 2D plane? Or?
So there is a result actually also by Anastasia Sideropoulos and Yuri Matusek. They proved hardness result even for the 2-dimensional plane in case of multiplicative embedding. Right. So I think there could be some factor n approximation, but it's pretty bad. Yeah. They didn't consider outliers though. Yeah. But if you want to do that without outliers, it's hard.
And I forget, do you, the number of outliers, is that a rigid bound or like, is it a hard bound on number of outliers?
So this is like a decision problem. One can ask, so once we run this algorithm, right, it basically either decides that KFC are parameters, that the initial object didn't have a right, subspace of vertices of size k such that upon removal, we have a C embeddability, or it outputs an approximation for the outlier set and the embedding.
Fair enough. And would you have hardness results for an exact number of outliers? So if I said you have to take only C outliers?
So C is the distortion constant. You mean hardness?
Oh, I see. So
can we take out K outliers? No, yeah, we don't yet. Maybe in the future. That is actually could be an open problem. The hardness result for the exact number of outliers.
Fair enough. Cool. Any other questions? Cool. Thank you again.
Thank you.
And we can move on to the last talk of the session. In fact, the last talk of the conference, which is always a good place to be. after a very satisfactory conference. So the last talk, Ishan, do you want to share your screen? Fair enough. Perfect. So the last talk of the conference is going to be by Ishan Agarwal, who will tell us about embeddings again, but this time of flat tori. Go ahead, Ishan. Ishan, you're muted, so you want to.
Oh, sorry. Right.
No.
Okay. So, right. Hi, I'm Ishan, and this work is on nearly optimal embeddings of flat tori, and it is joint work with Red Regev and Yi Tang. So firstly, what is a lattice? A lattice is just the set of all integer linear combinations of some basis vectors in Rn. So here we have an example in 2 dimensions. And one thing we will care about regarding lattices is this parameter called lambda1 of L, which is the shortest non-zero length in L. So here it's this distance. And we'll be calling this the scale of the lattice, and why we care about this will become apparent as we go. So what do these lattices have to do with tori? So a flat torus, Rn over L, is the quotient space of Euclidean space by some lattice L. And this is a generalization of like the usual R2 over Z squared torus. And what are the elements in this space? So the elements in this flat torus are cosets. So you take a point X in Rn and consider the coset X plus L. And these are your elements of your space. So maybe we start with a 1D example. And we do need to define a notion of distance on this flat torus. So here we have a one-dimensional flat torus. What does this mean? You take the real line and quotient it over the set of integers. So now like 0, 1, 2, and all they're all identified. And if we ask what's the distance between say 0.2 and 0.8, well, if this was just a real line, it would just be 0.6. But it's not. It's a torus where we've done this quotienting. So what we need to do is we need to consider the coset 0.2 plus z. This means like 0.2, 1.2, 2.2, and so on. And also the coset for 0.8. And the distance between these 2 points in this torus is actually the minimum distance between their respective cosets. So you see that between 0.8 and 1.2, you can manage to get a distance of only 0.4. So the distance would in this case be 0.4. And similar thing happens in 2 dimensions. So we just show an example. So we have this lattice as illustrated roughly by the dashed lines. And what's the distance between the blue and the red point? Well, it's not this because it's quotiented. And we have to consider the cosets. So when we consider the cosets, we see that actually there's a shorter distance. And as we already saw in the previous talk, we have a notion of distortion, and it's just the multiplicative distortion that was defined. It's the factor by which our mapping changes the distance between 2 points. So if you have a mapping F between metric space M1 to metric space M2, the distortion is the ratio by which it might change distances. So the question we consider is, how can we embed flat tori into Hilbert spaces with low distortion? And this question was introduced by Cote and Nauer in 2005. And they showed a lower bound whereby they showed that there are lattices such that you will not be able to embed with less than root n distortion. But they could only in the general case get an embedding of exponential distortion. And in 2010, Haviv and Regev showed a much better embedding, and they managed to embed with in order n root log n distortion. However, this is still missing roughly a root n factor. And they do actually have this embedding work in root n log n, which is almost right, but it only works in very special cases. And our contribution in this work is that we show for any arbitrary torus, we have this metric embedding, which we have constructed and which embeds from the torus to a Hilbert space with distortion root n log n. So one very important idea which was introduced in this HR10 paper is we can use Gaussian functions as the space we embed into. Like we take a point X in Rn, or Rn over L actually, and we map it to a Gaussian function centered at the point. So let's be clear here, what we are doing is we are taking points in our space and we are mapping to a function space. And why might we do this? Why might we care about Gaussian functions? Well, if you have 2 points X and Y, like, let's just think on the real line itself. And we have the Gaussian function centered at X, we have Gaussian function centered at Y. So the distance in the function space, as long as these points are close together, behaves well. Because as long as these points are close together, we can calculate that if we move x slightly away from y, then the distance in the L2 space also increases proportionally. So this behaves very well as long as points are close together. But once x and y are far apart, now the distance seems to have saturated, right? Because if I move these points further apart, the distance can hardly grow anymore. There's not much room to grow, right? So
the distance is being measured in like total variation or something?
Is the L2 distance of the function. So it's you can take the integral of absolute difference.
Okay,
basically.
got it.
It's a shaded area. Okay. So this idea was used in HR10, and they use, I mean, you cannot use a single Gaussian. It's not periodic for one thing, but you can use multiple Gaussians, and with varying scales of the Gaussians. They managed to get this really good distortion. But the problem, as we saw, is their embedding behaves, I mean, in principle, it behaves like the single Gaussian. After you go beyond a certain distance, it's just going to saturate, and it's not going to capture further increase in distance. So if you have any distance in your torus which has more than poly n times lambda 1 of that torus, then that distance is just not going. You cannot capture those large sizes with this embedding. So what might you do? What you can do is you can say, fine, I have this torus. Maybe it has large distances. Let me break up this torus into some direct sum of tori, and I'll do this somehow such that each torus has distances only of a certain scale, and then I'll use this embedding and I'll put them together, right? So this can be done. So here we have a 2D example. So let's say in the x direction we have small distances. In the y direction, distance could be arbitrarily larger than the x direction, right? And lambda 1 is in this direction. So I want to capture distance between the red and the blue points. So if I use the HR10 embedding directly, it'll capture x distance well, but it might do really bad on the y distance, right? Because that's way more than poly times lambda 1, say. So the idea of breaking it into direct sum of two tori is, let me look at the original torus. I'll use the embedding that's known, and I'll get the x component. And for the y component, I'll just project out the x. I'll take this torus, I project perpendicular to this sublattice. This is a sublattice, and I can project perpendicular to this to get a lower dimensions lattice, right? And now I just have this y dimension. And here, what is lambda 1 of this? It's big. It's big compared to any possible distance here, right? So I'll be able to do the embedding for this torus, and I'll be able to capture this distance as well. So this seems well and good. What's the problem, right? So if you recall, they were losing an extra root n factor, and actually inside this example, you can see where that comes from. So the problem is the x distance got captured once here. The y distance got captured once here, but we have to capture all possible kinds of distances. So the y distance might not have been huge, right? Maybe it's quite small, and it gets captured here once, but it also gets captured here once. So we captured it twice. And if you had n dimensions, you might have to end up capturing some distance n times, which is exactly where that root n comes from. So you might say, okay, fine. Why don't I just do the following? I managed to get just the y distance here, right, by projecting. So let me just project onto the x-axis. I'll get just the x distance. Okay. But we cannot actually do this. So if I actually try projecting onto the x-axis, what you see is all the points just fill up the whole x-axis, and I lose all information. And the reason that happened is that projecting onto the x-axis is not, that direction is not perpendicular to any sublattice. The y-axis is perpendicular to this sublattice, and projection is only allowed perpendicular to some sublattice. So now our idea was we can get around this. What we do is we don't go all the way. Instead of projecting completely onto the x-axis, let me just go halfway. Let me just scale everything down in that direction by, say, a factor of half. So now I'm doing the old thing, the old idea, which is just I have the original lattice, but I've scaled down the y direction by a factor of half. And here I have the projection onto the y direction. So here I get the x distance completely without any scaling down. Here I get the y distance completely. And here, whatever that y distance might be, big, small, definitely I'm going to be able to, I'm only going to get an extra half y, right? And in the n-dimensional case, what this corresponds to is, at worst, in some direction, that distance might be captured multiple times, even n times, but it will be scaled down more and more. It will be captured only once wholly, captured once with factor alpha, in this case half, and then in another piece by alpha square. Another piece will be scaled down alpha cube, and so on. So you get this geometric series, right? So no distance is being captured too much. Even if it's captured too many times, you're weighing it down. So finally, the proof proceeds in 2 steps. We first break up our torus into these multiple tori. Somehow we control the scale so that the different scales are in different tori. And then we manage, the main step is we manage to get a constant distortion here. We take the torus and break it into separate scales. And because of this geometric series damping down effect, we get a constant distortion embedding in this part. And then recall that the HRT embedding actually works really well once scales are controlled for, as long as there's no saturation issue. And so putting these two together, we managed to get root n log n distortion embedding. So this is the broad framework of our result. So yeah, I encourage you to look at the longer talk. So there are lots of subtleties actually in these steps which we discussed. So thank you for listening. And any questions?
Thanks, Ishan. Any questions for Ishan? Interesting. So, Ishan, is there any anything known for like higher dimensional sort of toruses, whatever, higher dimensional analogs, higher dimensional lattices, and
Right. So this is, I mean, I just showed you
for an n-dimensional lattice, right?
Yeah, this is for any lattice, like arbitrary lattice. This is just shown in the 2-dimensional case. So if you imagine 3D or so you'd have a Z.
Yeah. Okay. No, sorry, I don't know what I was thinking.
No, it's right. This example can be generalized.
I got it.
Right.
So what would be? Is there a natural next step that you would consider?
So this resolves this specific problem up to almost type factor. There's only root log n factor. But one thing you can ask is, well, this is a uniform like bound for any lattice, and we're not saying that. I mean, some lattices will have good geometry, which will actually allow you to embed in much less than root n. This root n is not for typical lattices. So you might say, okay, maybe there will be some special class of lattices. And in particular, there are natural special classes of lattices that people care about. And for example, there's this thing called stable lattices, which are guaranteed to have good geometry. And that is actually known that there you'll be able to do root n embedding with no difficulty. But with more specific information on the geometry, like considering other lattice parameters, right? Maybe we'll have parametric result.
Cool. Thank you.
Thanks.
Other questions? If not, maybe let's thank Ishan and all the other speakers of the session. Cool. Yarek, all yours, man.
Thank you. So I thought since this was the last talk of APPROX that maybe I will take this opportunity to thank everyone who contributed to this conference. I think it went pretty well. I'm particularly impressed by that. The speakers all managed to give some meaningful talks in these 10-minute slots. So that was a positive surprise to me that all these talks were actually pretty valuable, and I enjoyed watching them. Of course, we should thank the other people involved, the program committee for selecting the program and the reviewers. Well, I should also mention some people who helped me with coordinating this online event. So Lativek was helping me along the way, and Andreas Feldman was assisting me with these online events here. Kuba Ternavsky was our YouTuber, putting all these pre-recorded films on YouTube. I should also mention Yinted Lee from University of Washington, who arranged registration and also these Zoom sessions by the University of Washington. So, I mean, everyone worked together fantastic. So thank you all. I hope you enjoyed the conference.
And thank you, Yarek, for chairing it. It's a real pleasure to have you here.
Okay. So, thank you. I hope you attend future APPROX conferences.
Okay. See you guys. Bye-bye.